All right, class, let's begin here. We are in chapter 10. Just a quick review. We didn't have homework. Well, I gave you guys homework just yesterday. Started on it. I'm going to give one more day for homework. So 10.1 homework is going to be due. Let's see, we have class. I'm going to make it due Wednesday of next week. We good? Just to give you guys a little time.
I did what they said to do in the book, but I got a very different answer.
Ooh, okay.
So I don't know if that. 21, 25.
Okay.
21, 25. Okay.
Yeah.
So
If the angle is too like large, then it's obtuse, and you have to add 5 for the, and if it's a so that's probably what messed it up.
Cool. Awesome. So real quick here, review really fast 10.1 and we'll jump to 10.1. We just didn't do one extra little thing in 10.1, but I want to get through 10.2 today. So we're going to jam kind of quickly here. So 10.1 is all about lines, all the stuff that we have not done about lines so far, and we're going to connect them to something. And so just a quick review. No numbers, just concepts. We good? For the 2 people down here the other day. So real quick here, bless you, bless you, bless you.
That was like the most aggressive scene I've ever heard.
So here's what we did in the first piece of information from 10.1 is we're trying to connect lines, guys, real quick here, trying to connect lines to angle measurements. So lines and angles are connected now. And so we have this theta that connects the line. Now theta is going to be, it's called inclination. So if there's an escalator that's on the ground right here, and there's an escalator that's going up like this, right? That is called an angle of inclination. Are we good? So it's just from the bottom, and we use it so much because if you look at an airplane flying in the sky, and if you're on ground level and you look up, you're going to have angle of inclination again. We good? So very important stuff here. The only other thing that happens here is if it's above 90 degrees, if the line is coming down this way, what we do is we still look at the angle of inclination from the positive x-axis. Okay, we good there? That's angle of inclination. And there's a formula for it. And there's a video. The next thing that we covered. Is there a video? I'm not sure if there's a video. There may be a video.
Okay.
Okay, the next thing we covered was 2 lines now. So instead of 1 line, we got 2 lines coming in.
What's the formula for the 1 line?
The 1 line formula, anybody?
It's like theta equals 10 negative 10, the inverse, theta equals inverse 10 times slope. Do you say inverse 10 or 10 inverse?
And we say even tangent. So the inverse of tangent or
Okay.
tangent inverse is fine. Yeah. We use the full name, even though we abbreviated for notation purposes.
And
So
if it's obtuse, you add pi. Or 180 if you use the pi.
yeah, let's do that. Let's kind of put that in here. So let's see. Theta is equal to tangent inverse of our slope. And that is it if what? If theta is less than 90 degrees or you have an acute angle. Okay. Ding, 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 ding. Theta is equal to.
Okay.
Yeah, the sign should be.
Oh, yeah, the sign's wrong.
Yes.
Thank you. Yep. And then what do we do here? This is theta is going to be tangent inverse tangent of the slope plus 180 or pi, depending which measurements you're in. But in the homework, I think all of them were in pi
They're
measurements,
all
right?
wrong,
Oh,
so.
it's hinted for the 21, 25, it's hitting radii and
So there's radian measurement and degree
Well,
measurement.
Okay.
Okay, this is for theta that is greater than 90 degrees.
Wait, it's plus pi, which one's that? Okay.
That's radian.
Pi would be radian measurement and 180 would be degree measurement. Okay, there's that. That kind of gives us an understanding of it. Okay, we're good there. Next is the angle measurement between two lines. So that's one line. We go two lines now. So we have this on our hands, and we have two lines coming together. We've got this one and this one coming across. And our measurement is always going to give us the smaller angle. Notice on vertical lines, there's always two angles. And the formula for it is crazy
Theta
formula.
equals tan inverse times parentheses and then absolute value signs. M2 minus M1 over 1 plus M1 times M2.
Okay, boom, that's crazy. And we did one example like that, and that was done,
Yeah.
right, with class. So there's that, and that one works all the time. That one, you're always going to get the smaller angle. If you want to get the larger angle, you subtract from 180, right? If you need the larger angle. Good. Tan is a trigonometry function. We're not going to learn about it. We're just going to learn how to use it. So it's just this one part that we learn how to use it. So it is on your
1 plus M1 plus M2 or?
M1 times M2.
okay. Last part that we did not cover. Dun, dun, dun. Here's this little part. One last thing with lines that we haven't covered in algebra 1 or algebra 2.
Wait, what do you call that angle right there?
Theta. This little guy is
All the
called.
angles are called theta.
There it is, theta. Okay, we're good there. That was a quick review of what we did on Monday.
Just never go past the dark ages.
We love them. Okay, now we got one last thing is the distance between a point and a line. So I can spell distance between a point and almost squeezed it in there here, but it's gonna be a line. Okay, so what are we looking at? We're looking at something like this right here. I have a line that's coming like this. And I have a little dot that's right there. Just sitting there in space. Check something real quickly here. Okay, so one little thing that happens here, we're also trying to find the smallest distance. So you guys talk to me here. Smallest distance? I don't think so. So smallest distance? Smallest distance? No. Maybe. Smallest distance? Smallest distance? So line 1, 2, 3, or 4 gives me, looks like the smallest.
2 or 3?
2 or 3?
I think 3.
I think 3. So notice what happens with 3. There is exactly a 90-degree angle with that line right there. Interesting. So if I can figure out where the dot is and draw a perpendicular line to my line, I give myself my smallest distance. Again, I'm just kind of throwing the formula out there because it's kind of difficult to get to. Here's our formula, and we're going to just try it for one problem. The distance from a line to a point is the absolute value of A times x1 plus B times y1 plus C. And we'll see what all those things mean in just a second here. with the square root of
Is this the absolute value of A?
absolute value of
Oh,
A.
no.
Oh, I
Uh-huh.
wasn't looking. Oh, God.
So yeah, this little guy's absolute value.
Okay.
Fine, that's fine.
Crazy, just the little formulas here.
That is like absolute value, that's the top, right?
Yeah, absolutely, just on top.
Okay.
Okay, so what are these A, B's, X1s, Y1s? So X1, Y1 is the point. And our equation is AX plus BY plus C equals 0. That's our line. And so our line equation is set to 0. When we get that, then we get ourselves our ABCs. Okay, the good thing is that's it. Those are the three things that we haven't covered in algebra so far. So it's the angle of inclination, the angle between two lines, and now this, the distance from a point to a line. Okay, let's try one here. Try an example here. Example 1.
Oh, can you go back?
I can go back. And you guys, real quick here, can you guys see red pretty good on the board?
Yes.
Yeah. See that one?
Maybe I'm just the only one who thinks red.
Okay.
Do we not use the X and the Y as a line equation? Because we're using the X and the Y work from the point, right? Not the
Yeah,
line.
because the X and the Y are variables. Because
Right,
once you
okay.
introduce variables into it, then you're looking at multiple points. All right, find the distance. Here we go. Find. Between 4, 1 and y is equal to 2x plus 1. And we can draw it out. If you guys can draw that out just a bit here. All right, if I was to graph it just to sort of see it, that's all. So I'm thinking 1 here, and I'm thinking 1, 2, 1. And I'm thinking 1, 2, 3, 4, 5, 1. Okay. So my point is going to be 1, 2, 3, 4 up 1. There's my little point of blue. My line itself is, if we can remember how to draw lines again here. So I think we cross the y-axis at 1. Up 2 over 1 is my next dot, which is right here. And boom, perfect. And we can repeat it if need be. Okay, so what we're trying to find a line that's going to connect this guy in a perpendicular. I'm going to move my line like this. I think it goes like this. I want a distance of that line right there.
So
Okay, big formula, but let's
we
go.
want to move the Y over first.
Oh, that's right. Yes. Okay, the point is nice. So if we want to label x1 is a 4, y1 is a 1. Are we good there? Absolutely need the same sign and equal sign. So we're going to move everything over. So let's see, minus 2x minus 1.
Or just -1.
That's true, huh? It could go one way or another, huh? That's interesting. Okay, so Abby,
It'd be the
you
same
subtract the
thing
Y
as
over.
absolute value size, right?
Good, that's exactly why.
From the square root.
So I think I'm gonna do it that way, yeah. So 0 is equal to 2x minus y plus 1. Is that good? So I got myself, give me my A value,
2,
B value,
1,
and C.
1.
Awesome. And let's start plugging into an equation here. Absolute value of
2 times 4 plus 1 negative 1 times 1.
Yeah, I'm gonna put plus sign. I'll just put a negative one in there. So plus -1 times 1.
Plus 1.
All over.
2 squared plus.
The square root of 2 squared.
Mhm.
Yes.
-1 squared. Okay. Hey, that's easy enough. All right. To develop the formula it takes a lot, but to use the formula, no problem. Just like computers, right? I mean, computers. Unless you're a computer engineer, you don't know exactly how a computer works.
No.
But can you use it? Absolutely can use it. Okay, all yours for the answer when you get it.
All right, can you use calculator?
You can use calculators on it.
It's 8 divided by the square root of 5.
Ooh, awesome. Okay, so that's 8. Oh, that's right. There's 8 plus 8 minus 1 plus 1. That's 8.
The absolute value is
True. Yeah, absolutely. And then eventually,
5.
No, 8 over the square root of 5.
yeah, because that's 4. 4 plus 1 is 5. Okay, and this one, let's go.
2.236.
Are you sure?
5, yeah.
Okay, gotcha. And then 8 divided by square root of 5.
Yeah.
What's the answer there?
3.5.
Okay. 3.57. Okay. How about 3 point? I don't know. 6 is fine. 3.6. You have to just check the back of the book to see if they. Let me check the back of the book. Let's see what they do, what they go to. 10.1, 10.1, 10.1.
When I checked for the 10.1, they went way further than I thought they would.
Oh, really?
Like one of the answers was 2.1112.
Whoa,
Lots of
they're
decimal
going crazy.
places.
1.3152.
Yeah, they like to put a lot of decimals.
Gee whiz. Okay, I'm gonna go like 1 or 2 decimal places is fine. As long as you're there.
Okay. Thank you.
Okay, are we good there? Distance between a point and a line. There it is. Last thing from point 1, point 2. Okay, so these are kind of topics in analytic geometry, right? So that's one topic. Lines are kind of like one topic by themselves. We good? Now, starting 10.2, 10.2, and 10.3, and all the way through. I think we said we're going to do only what, 10.5 or 4? What did we say? Okay, from 10.4 to from 10.2 to 10.4, we call this conic sections. See, Joe's excited. See, they're called conic sections, or for short, kind of like the slang term, just conics. Whoa, what is that? Okay, so. Okay, good there. Let's intro, because this is a cool little thing to sort of see. I want to know the. Thank you, Brad. Oh, this will be cool. You guys ready for this? I'm gonna put some stuff on the board. You guys tell me what is the overarching theme or the word that describes all of them. We good? So for Hawken just came in here. I'm gonna put some stuff on the board. You guys tell me a word that describes all of them. We good? So.
Yeah. Oh my goodness, you're right. The Latin person was the best friends. And.
Oh, see, oh, it all relates. Okay,
Okay, cab.
they're wedding.
Transportation devices.
Oh,
all have an
They're all modes of transportation.
They all have an
Scooter
engine.
would still count as a mode of
Oh,
Would that be considered a vehicle?
Automobile.
It would be.
Transportation.
No, because that's the motor on it. Huh?
But it depends.
With like engines and stuff, well, both stuff.
Movement.
They can't have.
They can't.
Would it be like that,
All of them.
motorboat?
Motor.
Motorboats, okay.
All
Well, now they have
modes of
engines.
transportation.
They all have an engine.
That's my final.
Oh, I have an engine.
I mean,
Overarching?
What if it's a Tesla?
Oh.
It still has an engine.
Yeah.
Yeah, it's just an electric engine.
Their vehicles.
How do you-
It's not like your class.
How do you spell vehicles?
HI.
No,
CLE. S.
Yeah. So cars, trucks, motorboats, all those have this overarching thing, and we can just call it vehicles, right? And vehicles, do vehicles require a motor? I assume, right? I assume, right?
Actually, what about a sailboat?
Sailboat, okay, that's interesting. Okay,
Depends who you define vehicle.
right, yeah, because it's a category, right? It's a category as
I
opposed
guess
to a.
vehicle, you would normally think that it would have an engine. You wouldn't say, would you say that like a carriage is a vehicle? I don't think so.
Carriage?
I don't
Yeah,
think so.
carriage or vehicle?
It's only one horsepower.
Yeah, exactly.
It's a mode of transportation, but I don't think it's a vehicle.
So it's
I think
a line
vehicles
of
are
We should
vehicles.
look at the definition of a vehicle.
Yeah.
Should.
not right
You
now.
should. Not right now. So now the question is this, in mathematics, is there something that binds, this is kind of cool, I think it's kind of cool. Something that binds a dot,
The answer is yes.
a line, oh, two lines. And then circles, there's a circle, or at least a wannabe circle. Did you guys ever learn about something called ellipses? Did you guys ever see ellipses? Ellipses,
Like on those such things, a circle?
whoa, that's interesting.
Technically, your circle is also like, so we're gonna ignore that.
Yeah, ellipse is gonna stretch circle, right? It's an oblong circle.
From every point?
And let's
Yeah,
see.
yeah, circle, yeah.
Exactly.
No, we talked about this like every day in English. like,
Yeah.
Ellipse, oh, hyperbola. Hyperbola is kind of fun. It goes like this. It's the exact other side of an ellipse. The ellipse would be right here. That would be the ellipse right there. And the hyperbola is going the opposite way. It hits it. And that's it, I guess, right? 1, 2, 3, 4. Ellipses, conics, parabolas. Oh, and then the parabolas, that's right. And then we got parabolas. Parabolas are half. We've done parabolas already. X squared is a parabola. We can make them all multiple. That's kind of cool.
You could also draw them.
We could draw them.
Use all of them in graph.
They're all graphs, yeah, 'cause they're all
You know, when we
geometry.
went on this thing,
All right, let me give it to you, because we'll have to figure out. They can all be formed like this. So if you guys have a cone that's coming down like this, like that, and then you have another cone that's coming up like this, and I got another cone like this.
Hourglass, can you drop me?
Not yet, but can you guys point out for me, where is the point? Where's the point?
In the middle.
In the middle. There's a point right there.
Oh, I see.
Oh, so it connects.
Anybody point for me a line, just one line?
Just one of the sides.
Yeah, one of the sides. There it is. One of the sides is a line.
And then both sides together is 2 lines.
Perfect. Yeah, if I do this here, that gets me my 2 lines. So.
Where's the circle?
Yeah, where's this? Whoa, yeah, where's the circle, guys?
They're cones. So it's a slice of the cone.
Oh, cool. Okay, the top. If you slice one of the tops just exactly horizontally, there's my circle right there. How do you get an ellipse?
Then wouldn't you cut it the opposite direction? Right?
No, you cut it in half, just go.
Oh, cool. Hold on. Noah says cut it in half, but hold on. If I cut it in half, just think of what happens here. If I cut this like this, just sliced straight down, and I turn it this way, the slice would look like this, I think. The slice would go like that and like that.
That's what I was saying.
Oh.
Oh, which one of these shapes is over here? right there. Huh? That's called a hyperbola. We'll talk
And
about
then
those.
You can see the two triangles.
Oh, hold on. Before you do that, Noah, how about this guy? That's just going to be,
Half circle.
yeah, that's going to be one slice. So a parabola really is just one slice down. Just don't go all the way down. We're good. In fact, a parabola, you can even slice it like this. Slice that and you get yourself a parabola on the cross section. Interesting. Okay, we're still looking for an ellipse. How do you slice it so you get an ellipse? Ellipse would be an
Slice it
oblong.
lengthwise,
Oh, cool.
like
No.
at an angle.
Noah says instead of the circle being sliced exactly horizontally, if you slice this guy like this, you get yourself the ellipse. It'd be a circle that's kind of elongated one of the ways. All right. That is super cool. It's kind of like the thing that encompasses all the stuff we've covered so far. It is the, what is it? It is the three-dimensional shape that covers all the stuff of algebra. Isn't that kind of cool? It's almost like you came to the end and you realize like, oh, that's the structure. We good? So now the question comes up in physics and stuff like that, right? Physics is kind of the question is, what is time? What is gravity?
What is gravity?
Isn't time determined by gravity?
Maybe.
Because I heard that before the Big Bang, if that is correct, the correct theory, I've heard that then everything, there was no time because all mass was in one area.
I don't know, philosophical, but I'm gonna just go with this here. So gravity. I'll let you guys just, if you're bored on a Saturday.
As I typically am.
So we're looking for the visualization of gravity. How does gravity, if you try to visualize gravity, what would that look like? We good? And if you're trying to visualize time, now there's dispute about what time is, but I'm going to stop there before we get too philosophical here. But it has maybe something to do with this cone. We good? And I'm just going to stop there. We good?
The latest to this, I just recently watched a video in which I was like, wait a minute, up and down concepts. It's just in the earth, but not actually up or down. And I spent far too long thinking about that. So like, this would distract me for ages.
I'm so sorry, but it's fun though. Okay, so we got the visualization of gravity. How do you visualize gravity? And physicists think about that, and they kind of think about it maybe a cone structure. So this little double cone structure.
I've seen that similar cone structure, you know, like the idea of a wormhole. Does that have to do with it, or?
That has some reference to it, yeah. Okay, so let's go with it here. So introduction of conic sections. There it is. Let's jam with 10.2. So that was the intro. Now this is, we're going to handle one of them. All right, real quick here, parabolas. I make sure I spelled it right, really. Parabolas, parabolas. We have been doing this all along, guys. Parabolas. An example. An easy example. X squared is a parabola. We've been graphing this. So, Mr. Ng, this is so easy. Just been X squared. That's it. We go like that. That's a parabola. And then do we know how to flip it the other way? By transformations. And negative X squared flips it the other way, right? That's easy enough. Okay. So then another example. So instead of flipping it down, I want a parabola that does this. Oh, is it a function anymore? Does it pass a vertical line test? Does not pass a vertical line test.
The vertical line has the 2 points.
Yeah, it goes to 2 points, but I still want this. I still want the shape of this.
Yeah.
Couldn't you slice it down this way?
I'm not slicing. I just took one of the slices, right? Parabola is one of the slices. All right, the equation for it is, interestingly enough, hold on, let's go back over here. This x squared, the equation for this guy is y is equal to x squared. Are we good? The equation to this guy is x is equal to y squared.
Oh.
It's a flip of the equation themselves.
That makes sense, I guess.
And let's keep on going. So let's do this here. First things first is,
That kind of, it's so simple that it wasn't.
so two things that we're gonna make sure that we get through here is this part right here. So first thing is, we're gonna have this little imaginary line in the back end like this. And this is called a directrix. Okay, we good there? There's a directrix line over here. And that is a line in which, let me explain a little bit later here. Let me do that first here. So the other thing is something called a focus. Focus is right here.
Okay.
I'll explain why this is important in life itself, and then we'll go from there. Let me see if they do. Let me see if they do actually define what a directrix is, as opposed to just a line here. Okay, let's go with it here. And then,
You get with the magnifying glass. That's the same idea.
almost like that, yeah. So let's talk about the focus first. The focus means this right here, is that the distance from this line here is going to be the same. I kind of drew it out. The directrix should have been a little closer here. It's going to be the same distance. It's way off, guys, way off. Let me move this closer. The directrix should have been. Yeah, the directrix should have been like right, almost like right. No, it should have been actually on the line. Guys, I'm so sorry. One sec, can we move this little guy here out? I want to move this out, just kind of like up to here. Sorry, I didn't draw it. This is my y-axis, this is my x-axis, and my still jamming with it here. I think my parabola is not well written here. Can I change it up on you guys again?
Sure.
I'm gonna put it back where it used to be.
Okay. So that's
Just
just
try
us.
using a pencil.
You're not using a pencil? That's
Mhm. Okay, not drawn to scale. How about that, guys? First things first. So what does the focus and what do the directrix have in common is the distance here is going to be also the distance here, even though it's not drawn to scale. So I'm going to put D1 and D1. Those guys are all the same. Good there. It's the distance away. So I'm going to do this one in red. Oh, no, actually, I'll do it in blue. So this one right here, this piece here, I'll call it D2. If you go straight from the focus to the parabola itself, it'll be the same distance from here to here. Here's another D2. Okay, so the distance from the focus to the parabola itself is the same distance if you go straight down to the directrix. Hey, that's weird. You guys remember how we looked at the distance from a line to a point? It's kind of similar, isn't it? Like that. Yeah, there's my There's my perpendicular line. Okay, we're good there. So first things first is why parabola is so important. Why do we use them? Why do we take an extra time to look at them? Is because of this as well. So whenever a trajectory of something comes in and actually hits a side of this, the bounce effect is that it always goes to the focus. That's what the focus is so important. So if I have another thing that's coming in, it's going to hit the side and it comes right back to the focus. Focus is sort of like that middle piece there. And anybody tell me what that does that look like? In real life, where something comes in and it I have it in my house because we used to have DirecTV.
Well,
Dish. Yeah.
Satellite dish, absolutely. So all satellite dishes are parabolas. And that's why we have this little thing that sort of sits in front. Why? Because all the
Oh.
Oh, I see.
That's actually.
all the stuff hits and concentrates at one single area, and there is your receiver. We good? And so you get yourself the, which is kind of cool. Okay, so did I ever tell you guys this story here? So long time ago, when my daughter was 2, I think. She's in college now, so it's been a long time. So we went to a small little theme park in Florida. It was just kind of fun. It was probably the size of SLOCA High, about that big. And so I'm standing here, and she's probably standing where the tables are. And there's this little ring right here, and it has this little dish like that, and it's sitting on a post on the ground. And then she's standing all the way over there, and she has a little ring right there. It's metal, and there's a little thingamajiggy like this, and she's standing here. And there's people walking as well. People walking across here, they're walking around, right? Because there's people walking.
So one of those things that you use to talk to each other.
Uh-huh. And what I did is,
Those are
and so I speak right into this. In fact, I whisper.
very- yeah, just bounces. I've used those. before.
Mhm. I whisper and it goes across right here and it hits through the, right, to the people, various people walking along, right? And why is it helpful? Because it spreads out, right? So then it concentrates again so that it hits exactly where you want it to hit, which is kind of cool like that. That's awesome. But what is it? It's 2 parabolas, right? Extending and then concentrating in one area. So anyways, pretty cool stuff. We good? What's another way that we use them is, see again? Telescopes.
I remember seeing a picture that like giant one, it's sort of where like it's just a giant.
The ones that
Talker
observe,
basically in the
the
ground.
big ones that observe space that have the big
Oh, the big
dishes
ones.
on them
Uh-huh.
that aren't like manually operated.
Mhm.
Yeah.
Like, maybe it's too much.
Or maybe just, I thought it was just dish that looks for sound from space, right? It checks for sound, but also,
Like, the big,
okay.
like, little cones, right? Like, little dishes that have like little. Those- I don't think those are cones.
The Death Star, is that what you guys talking about?
That is
Classic.
classic.
Wait, isn't that, yeah, it's kind of, though, because like it uses like some like light energy.
Uh-huh.
Boom, look at that. It's, well, it's like, so, it's like if you put a plate that's like 1,000,000 feet by 1,000,000 feet or something, not
Uh-huh.
literally, but, and it's concrete in the ground, and there's like a little like tower thing above it. With NASA fancy stuff on it, and it lights up and reflects
NASA
off of
fancy
that
stuff.
onto the thing, and the NASA fancy stuff. That goes out into space.
So
Yeah.
It like,
I know what you're talking about.
yeah.
They use the ones that use for space observation, maybe they're not telescopes, but they do use it for space observation.
Uh-huh. Gotcha. Okay. One more example that I thought was kind of cool is kidney stones.
Oh, God.
Oh,
Hello?
Yeah. So check this out. A doctor friend. So he says what they do is they do laser. And so they have a patient. I'll call him this guy. He's a box. Okay, we'll draw a little shape of a person, right? And so what they'll do is they'll have that right there. Now the laser. So what you have to do is you have to penetrate through tissue, right? And then you have to concentrate it on the other side, right? And so what you do is they figure out the place of the kidney stone, and they have this apparatus. They'll shoot laser here. Well, laser gets distributed. And then you have this right here. You have him laying down on the right here. I'll put it in red here. And so the laser is distributed, so it's not hurting any tissue, right? Because it's dispersed, completely dispersed into like micro values of itself.
But it could,
But then it like.
it could be
And then-
like Death Star.
It
They
bounces.
shot the laser somewhere else.
Oops. So they better be very clear where that where kidney stone is. So they shoot it, and it, especially like big ones that need to be.
So like, it passes through the body and then
It just destroys it. So they shoot it. It at least breaks up the kidney stone into small pieces,
oh, that's so interesting.
very very small pieces, and then so it doesn't even hurt the person.
Sounds like it's for like, it should be spot like laser eye surgery.
Hmm.
Lasers in your eyes sounds like really
My
dumb.
eyes are fine just the way they are.
Is LASIK done with laser?
Yeah.
Yeah,
I never knew.
laser, laser.
I don't know.
Because they know lasers in your eyes never.
And I wonder how LASIK actually works. Is it set up something along those lines, or is it just a laser to cut through something, right? Because with laser, you do have to stop somewhere, right? And this is the stopping mechanism.
No matter what, it's like the worst idea ever.
Except it works.
Apparently it works, yeah.
Okay, so let's go with it here. So let's go to formal definition of parabola. So we were going to call this the.
I wonder if first was like, I'm pretty sure we can get this to pass safely through your body. Let's just
Yeah, that'd be
find
fun.
out.
Let's just try.
You're not from death. You don't know what this does, so hopefully it'll be fine.
You know, class, real quick, one thing I did forget to mention, this is called the standard form. And then we'll kind of get to standard form of, I think it's just called conic sections here. Of any conic section. Sorry, that's the one I forgot to do, one last piece, and then we'll kind of do the other ones now. So we're going to go ax squared plus bxy plus cy squared plus dx plus ey. Whoa. It'll be a cool equation though once we see it here. Plus f is equal to 0. All right, coming back to this one, I should actually move this up. I should move it up to here after the conic. So all these conic sections that we learned about. If we go over here, this is the equation that gives all of them in a general form. So it's called general form as well. So real quick here, if I do this, let me erase a few things here. If I get rid of this stuff right here, this little guy with the x and the y and the f, doesn't that look like 2x plus 3y plus 4 equals 0? What does that look like? Y equals mx plus b. That's our line equation. Is that right? That's our line equation. That's cool. Okay, so let me do this here. If I get rid of this one, and this one, if I'm trying to solve for 2x plus 5 equals 0, that's going to give me one single point, isn't it? There's my point. There's my line. We good? So from these conic sections here, I have an equation for my point. I have an equation for my line, right? And I can just keep on going. And so if I do this, ooh, let's see, what can I get rid of to give me my equation of my circle?
Get rid of BXY.
BXY goes away,
BXY there.
right there. So plus F. Okay, everybody okay with that's an equation of a circle? I can just form it as x squared plus,
Should I be writing down all these different?
no, this is just, so x squared plus y squared is equal to 25. Anybody know what this is? What is an equation of a circle with radius? Radius 5. We good? So this is so cool. Not only do we have a figure that actually gives us all the different stuff we've covered so far, but this little equation just covered all of algebra 1 and algebra 2 right here. That's all you guys been studying right there,
Wow.
which is kind of cool. Okay, now let's get back to what we need to do. So we're going to concentrate on the parabola particularly. 10.2. We might actually even get to the first exercise problem. So parabolas, let's go with it here. Parabolas. What's the general form of the standard form? Standard equation. Perfect. We have to include the x squared. We have to include also the y squared pieces. Guys, good. Okay. All right, so get a few things here. So we have two different parabolas here. This one first is going to be x minus h to the second power is equal to 4. P. Again, this is the very, very general form. And we'll see how that looks like. P is not equal to 0. Now this one is going to have a vertical axis. This is the one with the vertical axis. And the directrix equation will take some extra time to get here. So it's going to be k minus p. So p can't be equal to 0. If it's equal to 0, then it doesn't work. We'll get there. Okay, next one.
So the direction is the directrix is
The equation for directrix. Yeah, y is equal to k minus p. Okay, next one. If we're going to go horizontally, here's my horizontal equation: y minus k for p, x minus h. Obviously, p can equal 0 again. Now this one has a horizontal axis, and we'll introduce it. We have 5 more minutes left here. Horizontal axis, and the directrix equation is, so the directrix line is going to be x now. X is equal to h minus p. Whoa. Again, looks crazy at first. We'll get there. Well, I think we're going to just spend another day on parabolas.
not that, not this last.
Okay, one more thing here. So at the origin. Oh, sure, absolutely. Yeah, please tell me that. So this guy here, let's put a little graph to it here. So the vertical axis just means you have like this. Go there. Horizontal axis means you're going like that, right? Either to the left or to the right, depending on the numbers. Okay, if you're exactly at the origin, that'll h is equal to 0 and k is equal to 0. Because H and K are just the movement up or down and left or right. So real quick here, at the origin, which we'll do a whole bunch of them at the origin. Origin, H is equal to 0, K is equal to 0. That's what we want to have. And you guys talk to me. The first one here. So if that becomes a 0, that becomes a 0. What does that look like?
Is HK a coordinate?
Uh-huh. Perfect, yeah. So let me go through it again. So at the origin, H and K are 0. So take those formulas that we just did, put a 0 for H, and we should get, looks like this. That's for the vertical axes again, right? And then if K and H is 0, this is going to be y squared is equal to 4px. This is for the horizontal axes. Okay, let's do one that we know. I'm going to take this one here, right? Exercise 1.
Yeah, we made it.
Hey.
Graph with a minute and a half left. Let's go. Uh-huh.
Oh, next, life is good.
I know, exactly.
We know it isn't good, but the next week after that.
Don't think about it. Don't think about it.
We actually,
Just don't
we have
remind
a
us.
full day on Friday.
We good? So graph a vertical parabola with p is equal to 1/4 at the origin.
I'm not gonna be here.
Okay, guys, ready? Minute and 15 seconds left here. Let's go for it here. So at the origin, we're going to do the easy one, the formula, which is going to do this one here. It's vertical, so we're going to do that one. So that's this right here. 4py, and p is going to be 1/4 for us.
So why?
Oh, that's so cool. We know that one. So yeah, we always thought of it as just y is equal to x squared, right, as a function, right? But a formula in the conic sections means that one has a p-value of 1/4. Ooh, real quick here. Can you give me the equation of the directrix?
Wouldn't it be the graph B the other side?
Say it again.
It's y equals k minus p, right? Y
Uh-huh.
equals k minus p.
K minus p.
So what's k?
K is how far you are away from the origin of K. K is your vertical shift up.
Oh, so 0?
0. So let's go over here. This should be a y equals, let's see, 0 minus 1/4. Is that right? So y, can you graph for me y is equal to negative 1/4? So if this is 1, if that's negative 1, we have a directrix line that's coming across about right here. And we're done for the day with example number 1.
All right, hey,
Cool, I don't understand. Exactly. That's why.
Wait till Friday and we'll put it all together.